Okay, in this video, I want to talk more about the Euclidean algorithm and to actually prove that it's correct. So the two learning objectives, I'm going to recast the Euclidean algorithm as a recursive function explicitly. And I want you to sort of understand how that might work. You can, if you're seeing recursive functions in computer science. And then I want to prove the correctness of the Euclidean algorithm, okay? So how can we understand the Euclidean algorithm as a recursive function? So a recursive function is one that calls itself, okay, to solve a problem. And here you can think, well, you know, it's like the Euclidean algorithm is a function that maybe I'll call GCD. And it takes two inputs, numbers A and B, where A is bigger than B, and it's going to output the greatest common divisor of A and B. And what are the steps that it follows? Well, the first thing it does is it tries to use the division algorithm to write A equals QB plus R. And then it says, well, if R is 0, I should return that the GCD of A and B is B, because of course B, in that case, divides itself, and it divides A, and no bigger number can possibly divide B, so it has to be the greatest common divisor of A and B. All right, what if B is not 0? Otherwise, then what we should do is we should compute the GCD of B and R, right? Promoting B to the new A and R to the new B, and return that. So that's the recursive piece. The GCD function calls itself on what we hope is a smaller instantiation of the problem, right? And we hope it's getting us someplace. So let's prove that this is correct. There are a couple of things I just wanted to have as ingredients to the proof. One is to just recall the definition of the GCD. It's a common divisor, and it's the greatest common divisor, so it's bigger than any other common divisor. And two, I wanted to have this little lemma that we proved in class the other day, right? So that if I've written A as QB plus R, and C is a common divisor of B and R, it also has to be a divisor of A. Similarly, if D is a divisor of A and B, it has to be a divisor of R. Okay, so let's see now how to use these facts all together to prove that indeed the Euclidean algorithm computes the GCD of A and B. All right, so let's see. For the proof, I guess let's go through the algorithm, right? So first, we'll say, let's note, as I did earlier, that if A equals QB plus R by the division algorithm, by the division algorithm, then, or and that remainder R is equal to 0, then B equals the GCD of A and B, because 1, B divides itself and no greater number, integer, divides B. Okay, so that sort of tells us that if we stop after step 2 in the Euclidean algorithm, we've returned the right thing. Okay, so next we'll show that the GCD of A and B is equal to the GCD of B and R. And that will show us that if we return the thing in the third step, we're returning the right thing. Okay, So let's see why that's true. Well, let's look at that little lemma. So the little lemma tells us that if we've written A as QB plus R, so if A equals QB plus R, if that satisfies the division algorithm, well, then it must be that and C divides B and C divides R, then C divides A. Okay, so that tells me then that the GCD of B and R, let me see, hold on. Okay, so what this is telling me is that I have C, a common divisor of B and R. It's also a common divisor of A and B. Let's write that down, i.e. any common divisor of B and R is also a common divisor of A and B, because it was already a divisor of B, right? So I just have learned now that it's also a divisor of A. And what that implies then, or maybe I'll say therefore, I know that in particular then, the GCD of B and R has to be less than or equal to the GCD of A and B, okay? Because the GCD of A and B, so any common divisor of B and R is a common divisor of A and B, okay? But I know that the GCD of A and B is bigger than or equal to all the common divisors of A and B. So in particular, it's greater than or equal to that one, all right? By the same kind of logic, what we'll see is that part 2 of this lemma, so I'm going to say by the same logic, part 2 of our lemma 1, I guess we only have one lemma, part 2 of our lemma 1 implies that the GCD of A and B is less than or equal to the GCD of B and R, okay? And I'm gonna leave you to try to work that out yourself. It's really the same as the argument we had before. We just had, so I'm gonna try, you should pause the video and see if you can write that out. But putting those two things together, what we know now is that therefore, the GCD of A and B has to be equal to the GCD of B and R. Oh, and that's what we wanted to show, right? Now there's one more little thing that we have to know, okay? We have to know that eventually this is gonna stop, right? We're not just gonna keep calling the GCD of another B and R and another B and R and another B and R. We have to know that it stops. And we can say that the algorithm terminates because the sequence of remainders is a strictly decreasing set of natural numbers. And by the well-ordering principle, if you have a set of natural numbers, It has, and it's non-empty. It has to have a least element, right? So eventually it can't go on forever. It will stop, right? Okay.